Hello, in this video we're going to look at formation of enolate ions. Enolate ions are important intermediates in a lot of reactions we're going to look at in this chapter. So we're going to go over two ways we can form enolate ions. And what I've got here on the left is acetone, a ketone, and sodium ethoxide. So sodium ethoxide and sodium hydroxide are typical bases we'll see in these types of reactions. And this can do a proton transfer here where we remove that alpha hydrogen, and that is going to give us our enolate ion. We'll unveil it in a second here. There's the enolate ion, and remember that has two resonance forms plus ethanol. Okay. Now, one thing about this proton transfer is that let's look at these pKa's. So this ketone has a pKa of about 20, whereas ethanol has a pKa equal to 16 to 18. It's probably closer to 16. Okay, so I'm just going to say 16, about equal to 16. All right. If you want to figure out in an acid-basic equilibrium whether the left side or the right side is formed, we ask the question, well, which side has the weaker acid? And we look at pKa's to figure that out. And this has a higher pKa, so it's the weaker acid. So the equilibrium actually favors I'm having trouble with equilibrium arrows here. Okay. Favors this side. Okay. So we're actually not making much of the enolate that we want to have here to go on and do other reactions. However, we can apply Le Chatelier's principle here. If this goes on and reacts with an electrophile, it's going to pull that out of this equilibrium. So we're going to reduce the amount of this product in the equilibrium, and that shifts the equilibrium to the right. Okay, so sometimes we can couple an unfavorable equilibrium with another step that's favorable, and it'll go in the forward direction. Okay. Now, however, there may be cases where our base will react with our electrophile more quickly than it will react with the ketone, or more favorably with the electrophile. And in those cases, we might want to use a different base. And so I'm going to show that different base. This base will either alkoxide or hydroxide. We'll see that actually a fair amount with aldol condensations and Claisen condensations. But I'm going to show you another base that we will use in some situations. Actually, probably the next video. And that, let me get my reactant back here, my ketone. And that reactant is LDA. And LDA stands for lithium diiso, two I's here, diisopropyl amide. And what it looks like is we've got the lithium cation, and that is bonded to, or well, it's not bonded, I guess, well, it's an ionic bond. We have two isopropyl groups here. Okay? It's a strong base, but because of these isopropyl groups, it's a non-nucleophilic base. So it's going to prefer, oftentimes nucleophiles, it can act as bases, but this one is going to prefer to focus on its nucleophilic side because of those isopropyl groups. And so it can deprotonate this position, and oops, that was 20. And what we can form here, and I'm actually going to show it, I think it's typically shown like this. And here the equilibrium greatly favors this side. Okay, so we make this enolate, and we call this a lithium enolate. All right, and then the other thing we make is diisopropylamine. Okay, now this has a pKa of about equal to 40. All right, so now when we look at our pKa numbers, we see that the higher one is on the right-hand side. And so this is the weaker acid, so now we're going to favor this side. So this is a much more favorable equilibrium for the formation of the enolate. And this is a proton transfer also. All right, so that concludes our video on formation of enolates. I think in the next video we're going to look at alkylation of lithium enolates, so having a reaction that can occur at that alpha carbon. All right, well, or what was the alpha carbon? I guess you could still consider an alpha carbon if you had a carbonyl there. So, all right, well, thanks for watching. Bye.